In this video, we will learn about the fundamental theorem of calculus. We have seen in a previous video the evaluation theorem, and indeed, we can derive the full fundamental theorem from the evaluation theorem. And actually, this is quite simple. It is just a change of notation. Let's look at the evaluation theorem again. So f is a continuous function on an interval a to b. Capital F is an antiderivative of little f, and so then we can evaluate the area under a curve as an integral from a to b f of x dx, which can then be computed using the antiderivative as f of b minus f of a. So that's a powerful method, and we have used it already in many examples. But now let's flip the notation. So what I do is I will use x instead of b and t instead of x. Okay, so let's just write down what this does. So this is integral from a to x, f of t dt. And according to the evaluation theorem, this would be f at the upper boundary, which is f of x now, minus f at the lower boundary, which is a. Okay, so I just changed notation. I didn't change anything else. But now I look at this formula and I differentiate with respect to x. So let's look at this. We have d by dx of this integral. I put it in a bracket, integral from a to x, f of t dt. So then this is the same as d by dx, f of x minus f of a. A is a constant, so f of a is a constant. The derivative is 0. So what this is really just f prime. But then capital F prime is little f. Oh, what happened here? Do you see what happened here? So I need to write this down again in different colors. So I do d by dx of the integral from a to x dt of a function f of t. And if I do the integral and then the d by dx, I get the original function back. Isn't that super cool? So this shows that integration and differentiation are really inverse processes. You do the integral first and then you do the derivative second. What you get is a function you started with. So this is rather cool. There's a very interesting geometric interpretation of this result. And for that I write down the formula again right here. And now let's look what this does. So let's first look at the integral from a to x, f of t dt. Right, so this is the signed area between the curve f and the x-axis on the interval a to x. So let's plot this out here, and I use t as the independent variable because this is what happens inside the integral also. And then I integrate this between a, which is a point here, and x, which is a point here, and of course I get the area under the curve. In this case the function is positive, so it is the area. But now what happens when I vary x, right? I can make x bigger or smaller. And if I make x bigger in this picture, then the area will become bigger. If I make it smaller, the area will become smaller. So we can ask about the rate of change of the integral if I vary x. Let me write this down. So the rate of change of the signed area as x is varied. But this is nothing else than saying d by dx. The rate of change is the derivative, as we learned earlier. This is actually this here. The rate of change of the integration as x is varied. But now this rate of change actually is equal to f itself. So here this point is f of x. So then this equals f of x. This is kind of surprising. Yeah, this is really surprising. So here you see the beauty of calculus. Let's state the full fundamental theorem now. Suppose f is continuous on the interval a and b. First, if g is defined to be the integral from a to x f of t dt, then g prime is equal to f. Second, if f is an antiderivative of little f, so f prime is little f, then the definite integral from a to b f of x dx is equal to f of b minus f of a. So, Tolo, Malo, I think we achieved something. Cheers. You will see that doing this is actually rather easy The only problem is kind of a bookkeeping problem. So you need to be aware which variable does describe what. So here's the first example. G of x is integral from 0 to x, 3t to the 4 minus 17t plus root of t dt. So what you should first notice is as a dt, so t here is the integration variable. So this is the variable against which we do the antiderivative, or if we integrate. And this arises here and here inside the integration too. Now the x here appears here and here, and this is the independent variable. Okay, now we are asked to find the derivative of the function g of x. So let's differentiate this using the fundamental theorem of calculus. Let's maybe just go back a slide and look at it again. So where are we? We are here. We have a function g defined as integral of a function f of t. And then the result says g prime is actually really just f. So to do the problem on the other slide, we need to identify f. So let's do this. So then f of t in that example would be 3t to the 4 minus 17t plus root t. And then by the fundamental theorem, we know that a g prime at x now is f at x. So easy. Then g prime at x is 3x to the 4 minus 17x plus root x. So it is really just a function which appears inside the integration, but now flipped. The variable t is flipped to the variable x. So that's the tricky part, to keep track which variable appears where. So here's another example with the function h, and h of y is integral from minus 8 to y sine x cos x minus 1 divided by x squared dx. Okay, so now the x is the integration variable, appears everywhere here, but the function h depends on y, which appears here. So if I talk about the derivative of h, I mean d by dy in this case, okay? We again need to identify the function inside the integral, so let's call it f of x. And by the fundamental theorem, we have that h prime at y, right? Y is now the new independent variable. This is really f at y. And then subbing in, this is sine y cos y minus 1 over y squared. And now you think, this can't be that easy, really. This is really all there is to it, to the fundamental theorem. Yes, there is. Let's look at a realistic example, like the measles pathogenesis. Pathogenesis describes the dynamics of, in this case, a virus in the human body. So it describes how the virus load changes as the virus progresses and multiplies in the body. The virus load becomes really, really high, and then the immune system kicks in and the virus load becomes small again. So here this blue function in this graph shows the pathogenesis of measles in a typical human person. On the x-axis we have time in days, and on the y-axis we have the number of infected cells per milliliter of blood plasma. So here at the first step the pathogen enters the plasma, which means the person gets infected by the virus, and then the virus load increases and increases, and then about 11 to 12 days the first symptoms appear, which is somewhere here in this area. And then the immune system kicks in and starts fighting the virus. And so here about the immune system kicks in, the virus can still increase a little bit, but at some point the immune system wins, the virus load goes down, and after about 21 days you are healed. So the curve describing this dynamics is given here. F of t is minus t cubed plus 20t squared plus 21t. So researchers found out that this is a good curve describing the pathogenesis. Now the immune system is triggered if the total amount of infection increases beyond a certain threshold. And the total amount of infection is the integral from 0 to t f of s ds. So in the end it is the area under this infection curve. So this area here, this would be a of t at time is equal to 12. So if this area exceeds the threshold a0, then the immune system kicks in. What is the rate of change of the total amount of infection at time t? So how quickly does this a of t change over time? So here I write down the formulas again. I have this little f of t, which is minus t cubed plus 20t squared plus 21t, and I have a, which is the integral of little f. What is the rate of change of the total amount of infection at time t? So what we're interested in is to find d by dt a of t. There are two ways to do this. The first one, the more natural one maybe, would be to take f, to integrate f, then find a, and then differentiate a. Okay? And the second alternative is to use the fundamental theorem of calculus. So let's do both. Let's maybe first integrate f to find a. Okay, so a of t is integral from 0 to t f of s ds. So let's write this out. This is integral from 0 to t minus s cubed plus 20s squared plus 21s ds. So I need to integrate the integrand and then I sub in the values. So then this is, if I integrate this stuff, minus a quarter s to the 4 plus 20 s to the 3, 21 s. And then I evaluate this between 0 and t. And remember, in this notation you do not need to add a constant because we have a definite integral and we give integral boundaries from 0 to t. So we sub in the integral boundaries. We have minus 1 quarter t to the 4 plus 20 t to the 3 plus 21 t. And then if I sub in 0, I get 0. So this is my function a of t. And then as a next step, I differentiate a of t because I'm interested in the rate. So d by dt would then be minus t cubed plus 20t squared plus 21t. So that is the solution. Okay. How does it look like if we use the fundamental theorem of calculus? So we know a of t is integral from 0 to t f of s ds. And from the fundamental theorem of calculus, we know that d by dt of a of t is actually f itself. It is f at t. And f is already given. So meaning this is minus t cubed plus 20t squared plus 21t. So now I leave it up to you to decide which way is easier. Let me summarize. Integration, differentiation are really inverse operations to each other. This integral here is an antiderivative, and we can actually use any a here. This should be a, not necessarily 0. And on the other hand, if we have an antiderivative, then we can express a definite integral to be capital F of b minus capital F of a. So very, very useful formulas, which you should remember and also be able to use, as we just did in the examples. Help me! Help me, Tolo! Tolo, come over! I'm under attack by a huge integral sign! Tolo!